Gaze-adaptive lenses for exploration of feature-rich information spaces. The ongoing digitalization of our daily lives leads to an increasing amount of digital data. A challenge is the visualization of digital information without the introduction of additional visual clutter. One common approach to reduce clutter are dynamic levels of details that can be controlled by panning and zooming the information space. While this type of interaction well allows the inspection of local details, it can affect the user's ability to develop a global perspective of the presented information. Interactive lenses that provide multiple views of the data simultaneously can help overcome this issue. However, these lenses typically require additional manual interaction for navigation and inspection. This can lead to additional cognitive load. In this work, we propose a combination of gaze and mouse input for the interaction with lenses. This allows controlling the lens with gaze while still being able to explore the map with the mouse. With a pilot study, we compare this approach to a mouse-only system in terms of efficiency, effectiveness, usability, and applied search strategies. He et al. Identified 7 basic categories of interaction that can be performed with interactive lenses. Filter, show me something based on a condition. Abstract, elaborate, show me more or less details. Select, mark something as interesting. Encode, show me a different representation. Reconfigure, show me a different arrangement. Connect, show me related items. And explore, show me something else. In our implementation, we focused on the first 5. The lens system consists of the overview map, which provides the distribution of all restaurants in the current map view, a lens indicator on the map, and the lens itself. It shows selected map content with a 3-fold magnification. It visualizes points for each restaurant's location and details at the point of regard. Specifically, names and star ratings are displayed only for restaurants located within an area of 2.5 degrees of visual angle. This spacing provides enough clearance to display this information without overlap. For an automatic label placement, we utilized simulated annealing, which is an efficient approach to optimize for reducing overlaps between labels and distances to their respective data points. In the mouse-only condition, the name and the star rating of a restaurant appeared when the location was in the center of the interactive lens. In the gaze-adaptive condition, the name and the star rating of a restaurant appeared on screen once participants focused on the location. In both conditions, participants could use the mouse to pan and zoom the map in the overview and interactive lens. A total of 20 participants took part in the pilot study. Our dependent variables for task performance include the number of locations found, the overall time to locate and memorize the 5 target locations, the ratio between completion time and the number of targets found, and the degree of fit between the participant's drawn map and the real map using bidimensional regression. The usability of the conditions was assessed with 2 questionnaires. We used the UAQ and the NASA Task Load Index. For eye tracking, our dependent measures include the ratio between gazes on the interactive lens and the overview map, gaze distribution in the overview map and the interactive lens, as well as gaze dispersion from the center of mass for the interactive lens in pixels. Participants were faster to complete the task and found more locations with the gaze-adaptive lens. Additionally, they were more accurate than those with the mouse-only lens in the mapping task. As expected, both conditions were rated as novel, since lens interfaces are not very common yet. For overall attractiveness, there was a slight advantage for the gaze-adaptive condition. In addition, participants rated the gaze condition to be easy to get familiar with. In terms of efficiency and dependability, both interactive lenses were rated similarly. Interestingly, participants found the mouse-only lens to be slightly more exciting and motivating to use. As expected, the distribution of gazes with the mouse-only lens is narrower compared to the gaze-adaptive lens, given that in this condition, our design did not render any labels within the periphery. This figure shows exemplary movement paths of the lens on the overview map. Also, the mouse-only participant only found 3 of the 5 targets. The amount of lens movement was higher than for the participant using the gaze-adaptive lens and found all 5 targets. The main benefit of the gaze-adaptive lens is the ability to determine content that is important for the user without explicit manual input. This can save space for better label placement and reduce visual clutter, because only focused areas need to be rendered with full detail. The results of the pilot study indicate that gaze-adaptive lenses can improve the performance in terms of finding locations on a map and mapping them afterwards. Furthermore, it seems that the gaze interface is easier to get familiar with and generally more attractive. We believe that this is the result from less mouse movement required. Here we can see both conditions side by side.